Hi, this is Dr. Xu teaching mine ventilation for mining engineering students. In this video, we will look at an example that deals with heat generated from a loader. So in this example, the loader rated power is 210 kilowatt, and the volumetric flow rate at the beginning of the roadway is given. The wet bulb temperature and the dry bulb temperature is given, and also, the wet bulb temperature and the dry bulb temperature at the end of the roadway is given. Some of the psychrometric properties are given in this table, including the ASV, that's the apparent specific volume, and the inverse of ASV is the density. So density equals to 1 divided by ASV. And the sigma heat and the moisture content. It's all given. This is for the start of the roadway, and this is for the end of the roadway. If the numbers in the table is not given, by using the wet bulb and dry bulb temperatures at the start and at the end of the roadway, we can find these values using a psychrometric chart. Question 1 is, what is the mass flow rate of air in the airway? So the mass flow rate equals to volumetric flow rate divided by ASV. So equals to 32 divided by 0.88 equals to 36.364 kilogram per second. The second question is, what is the total heat output in kilowatts and the evaporation rate in gram per second occurring between the two measuring points, so from the start to the end? So heat equals to mass flow rate by the change in sigma heat. That equals to 36,364 by sigma heat at the end of the roadway is 76.8, and sigma heat at the beginning of the roadway is 67.1. So that equals to 352.7 kilowatt. Moisture equals to mass flow rate by the change in moisture content. So equals to 36.364 by the moisture content at the end of the roadway is 18. At the beginning of the roadway is 16.7, equals to 47.27 gram per second. The next question asks, what is the maximum amount of heat that the loader could emit? Assuming 33% of diesel efficiency and assuming the loader is working continuously, what is the average engine load? So percent of the peak. The heat generated by diesel engine can be calculated from Q equals to rated power divided by efficiency by percent time available by percent utilization. So in this question, if we would calculate the maximum amount of heat that the loader could emit, the percent time available and the percent utilization, they will be the maximum of 1. So 1. And here the rated power is 210 divided by efficiency 33% by 1 equals to 636.36 kilowatt. So this is the maximum heat that this loader can be emitted. But actually the loader is emitting, so Q actual equals to 352.7 kilowatt. This result is from the previous question. Because the heat can be calculated as the rated power divided by efficiency by percent time available, but assuming the loader is working continuously, so that's 1, so 100%, by percent utilization, so they see the engine load, PT utilization, equals 352.7 kilowatt. and the rated power is 210 kilowatt, and the efficiency is 33%. We can plug in the number and solve this the engine load. So PT utilization equals to 55.4%. Next question. How much diesel fuel would the loader consume at this work rate over an 8-hour shift? Calorific value of diesel fuel is given, and the density of diesel fuel is also given. So the work rate we have calculated, so the average workload is 55.4%. Apparently, we need the equation that calculates the heat generated from diesel using fuel consumption. So Q equals to quantity of fuel by fuel density by calorific value divided by 1000 by total operating time. The heat generated from this diesel is 352.7 equals to quantity of fuel by fuel density 845 by calorific value of the diesel fuel 45.6 by 10 to the 6. Make sure you convert this million joule per kilogram to joule per kilogram. So that's why there is a 10 to the 6 divided by 1000 by 8 hours by 60 minutes in 1 hour and 6 seconds in 1 minute. So we can solve QF equals to 0.264 cubic meter equals to 264 liters. The last question used the approximation that 50 kilowatt of heat rises the temperature of 10 cubic meter per second of air by 1 degree of white bulb temperature. What would the return side white bulb temperature be if a second loader was to work in the same airway with the same work rate? So generating 352.7 kilowatt of heat, and the air quantity and intake temperature is the same. We know that the intake air quantity is 32 cubic meter per second. 50 kilowatt of heat can rise the temperature of 10 cubic meter per second of air by 1 degree of white bulb temperature. For 32 cubic meter per second of air to rise 1 degree, it requires 50 by 32 divided by 10 equals to 160 kilowatts. One extra loader will emit additional 352.7 kilowatt of heat. Therefore, it can increase the white bulb temperature by 352.7 divided by 160 equals to 2.2 degree. Therefore, the end white bulb temperature equals to 25.5 plus 2.2 equals to 27.7 degree. So this 25.5 is with only one loader working in this airway. With an additional loader working in this airway, the final white bulb temperature is going to be 27.7 degree. Okay, thank you very much for watching. This is Dr. Xu. I will see you in the next video.